Hi guys, welcome to topic 510 lenses. A lot of this is a refresh from GCSE, and some of the things we leave out at GCSE I'll put back in just to make sure and just point out the really obvious things. This one is a big building block leading to ray diagrams, so dig out your old GCSE notes on ray diagrams. That will be the next lesson we do, and part of that is again, very just top-end GCSE stuff, but also looking at magnification and powers. So dig out your old GCSE stuff, get familiar with it, and make sure you're ready for the next couple. So we start off the GCSE lesson with defining a convex lens and then defining a concave lens. So just to refresh your memory. Okay, so convex, now where people get themselves into a little bit of a dither here. In GCSE, we just talk about it being, I'll try and draw this as best I can, nice and symmetrical. That's appalling. These two should be equal, if I've drawn it correctly. It is correct, and they are equal in this diagram. Where people get themselves in a little bit confused is you can actually have a convex lens that looks like so. Now I'm going to exaggerate this massively to make it obvious. Okay, you can actually have a convex lens that does so. A good example of that is reading glasses. Now reading glasses are all determined by light coming in parallel, and if you don't need glasses, the lens in your eye does this for you. The light refracts in and to your pupil, through your pupil, into your nerves at the back of your eye, and that's all well and good, except if there's a problem with this lens, then it's your glasses job is to put that light in the right place for your eyes. Now that could be a question of them being at the wrong distance to each other. It could be the shape of the lens, of your eye, that is. And this is called, quite correctly, a corrective lens. Now concave, it's the complete opposite, if you like, where you can fit a convex inside a concave. An easy way of remembering concave is, of course, it creates a cave shape. Now lots of applications for both in everyday life, but at A-level physics you'll be expected to use your knowledge of both to talk about where the focus point is and magnifications, but we'll get into more detail as we go with that. Okay, when light is reflected, I equals R. That is not optional. Every part of the electromagnetic spectrum does this, and for some reason, when we draw a normal, a reflective plane, I should say, like this, for some reason people still draw normals at that angle and then start doing weird stuff up here. Okay, this is wrong. Okay, so if you had a reflective plane like that, your normal is going to be 90 degrees to it. There's my little right angle symbol, and of course you've got an angle of incidence, and that angle there must equal this angle here. So you would measure this one first, measure off to there, and your reflected angle light is going off there. It is good practice to label them incident and arrows, and arrow and reflected. Something we even teach to draw the line through. Normals always impact the impact plane as a term that gets used from time to time. So GCSE would make it really simple. We just talk about things being nice and vertical or horizontal. At A-level, things will be in 3 dimensions. Okay, so convex lenses, always a good place to start. Now there is a few bits and pieces we leave out at GCSE, but essentially the number one thing we don't make a big fuss about is the fact there are 2 principal focus points. Okay, 1 and 2. They are on either side of the lens. Now that's quite important for when we are looking at ray diagrams, because we need to know where these 2 are. Now, when the lens is symmetrical, nice and easy. Those two focus points are going to be at exactly the same distance to each other, which is fine. But if we start making this lens bigger, okay, more refraction occurs, and this focus point here will move in. So it might end up being here, and this is no longer equal. Now, what the typical question here would be is, let's try and ballpark this a little bit. So let's say that is a distance 1. So let's say that's distance 1 to roughly 3 times the original size. So you'd actually be moving the focus point in. So if I break this in now into roughly thirds, so we'd actually probably have our primary focus would actually be really in close. Now that's quite important when we start drawing ray diagrams, because that will really affect what happens to the image created. So not the object, but the image changes. So you'll hear me start using the word image and object quite often. So just be aware that the object is the real thing that we're looking at, that the light has reflected off. I think, have I got a ray? I don't think I've got a ray diagram picture in this PowerPoint. But if I was drawing a ray diagram, and just to remind you, ray diagrams, there's our lens, there's our reference line. Now a convex lens would be shown with an arrow up and down. If we have an object, and if you remember me, I like drawing Christmas trees. Okay, so light has come from every direction potentially, doesn't really matter to us. All we're interested in is the light that's hit this point here and reflected in this direction towards our lens. We're just dealing with reflected light off our object. Now we will go into ray diagrams in more detail later. However, if you can remember, so let me just quickly, let's say that's the focus point. So this will be a quick rehash on ray diagrams. There's our first line. Then we would have drawn one through the center and one through, now we won't go extreme, we'll keep them equidistant for the second, through that focal point, and then it'll be perpendicular, and here is our inverse Christmas tree. Now that is our image. In this case it's inverted, upside down. It'll be, well, it won't be magnified in this case. It'll be the opposite of magnified. Look, I won't spend too much time on ray diagrams in this one. Just I wanted to point out object, image, real, not real, and leave it at that. Key points to put in your diagram: focal length. I mean, it seems pretty obvious if you're dealing with a focal point, but the focal length is what determines things like camera lenses. So if you've ever taken a picture with a camera, this is all about what people often refer to as zoom, but when zoom is actually a little bit more complicated than that when we start stacking lenses together or powers together. So ignore that for the moment. This is actually about bringing the image into focus. So for an image to be in focus on your eye and the camera, same principle, the light has to meet at this point here. If the image is actually this big, so the focus is not quite right, this is what you would get as blurry. Okay, so this would be an out of focus picture, or someone who can't see objects without glasses on, they would see it as blurry image. The focus point could be in front of where it needs to be. Same problem, still be blurry. Okay, so I think I pretty much covered this in the last one, but importantly, as you increase the thickness, now remember that can be either side or symmetrical, doesn't matter. You can treat them as two separate entities or one whole big lens. But if you make them thicker, the focus point moves closer and closer and closer and closer. Okay, so very briefly, concave lens. I think you need to press the arrow a few times to get into the PowerPoint for this one, but essentially, just off the first image that comes up on the PowerPoint, this light is parallel to each other. We get to our concave lens and they refract, and now we have a problem that they are all diverging. They're all going off on their different directions. They're never going to meet. They will travel in a straight line forevermore and never come together, which kind of makes it a bit pointless until you think, okay, so where would these rays of light meet? Well, any time they'll meet is if we go backwards. Now, I'm pretty sure my diagram will have this better, but let's go backwards anyway and see how close we are. So if I go backwards, all of a sudden, I find a point where they meet, and funny enough, that is my focus point. And we'll go into more detail with ray diagrams where this comes into play. Oh, there you go, better diagram. I've just pressed the button and got the other diagram, so you've got a nicer picture. But the focus point's pretty obvious there. Okay, so concave lenses make parallel spread out as if they come from a principal focus. That seems like the same slide again. Okay, so if we were in class, this would be the activity you'd now be conducting. I will actually get you to do this one. It's a good bit of practice with the light boxes, just to make sure you know how to move light around. Which is effectively all lenses are. It's just for changing the path of rays of light. Not to curve light or anything nonsense like that, just to change the path of a ray of light. Of lenses, like I said, it is very much a carry on from GCSEs. There's a lot of GCSE content in there, so hopefully you're relatively familiar with it all. Make sure you add the key components to your revision sheet, but otherwise ray diagrams is your next one you need to move on to.